All right, now we've spent a lot of time talking about LTP, right, long-term potentiation, but now let's talk about LTD, long-term depression. You've already seen this in the cerebellum, and we'll bring that example up again. But this also happens in the hippocampus, right, from those CA3 to CA1, the Schaefer collateral connection there. So we'll take a look at that as well. I think the first question to answer, though, about LTD is the why. I think you could understand why it would be a good idea to strengthen synapses, right, in terms of encoding information, place information like we talked about, cause and effect information. But why would we ever want to weaken a synapse? Well, I think the idea is what would happen if we were to only strengthen, if synapses only got stronger. I think you could imagine that at some point, right, this effect would reach a ceiling. Like this effect would top out, right? There'd be some limit to it. This effect would reach a maximum capacity. And if that were the case, and now all of a sudden new information needed to be encoded, in a circuit where LTP has already reached its maximum, there'd be no new ability to encode any of that new information, right? So instead, synapses have to be dynamically strengthened and weakened to adapt, right? So synapses must be dynamic, meaning that they're changing, right? Something that's static stays the same, but these synapses will be changing dynamically. How do we say? To adjust. It's supposed to be adjust. To new info. Again, this feels vague, but the idea here is that if you've sort of maxed out your ability to perform LTP, let's internalize some of those receptors or change in some way, right, that potentiation and decrease it such that now if there is new information to be encoded, there is capacity to perform LTD, or excuse me, to perform LTP. So what we'll talk about now is this pathway that was demonstrated in the Schaefer collaterals. Okay, so this is that same synapse that we've talked about, and the alignment or the experimental setup is off to the right here, so we can see it's the same CA3 to CA1 pathway. We've got a presynaptic CA3, and so this is our presynaptic CA3, our postsynaptic CA1, and stimulating the CA3 and then recording postsynaptically from the CA1. Okay, so this setup doesn't change too much from when we looked at LTP. And so what we see here is that low frequency stimulation, as opposed to, remember, that HFC, the tetanus that we would apply, that's what LTP was, but an LTD, low frequency stimulation. How low are we talking about? Well, 1 hertz, right? A hertz is a measurement of frequency, so 1 stimulus per second. That's a 1 hertz stimulus. For about 10 or 15 minutes is enough to induce LTD. So the idea here is that this stimulus is going to be given every second for 10 to 15 minutes. Okay. And what we see after we do this is a depression in the EPSPs of the postsynaptic neuron, right? So what LTD is a depression in the postsynaptic neuron. As measured by its EPSP, right? That is the membrane potential change was at some level, and now it goes down. We get a smaller change. Okay, so although the postsynaptic neuron is still moving toward threshold, it's just moving toward threshold to a lesser degree. It's interesting if you look at LTP and LTD sort of together, we can reverse LTP with LTD and vice versa. So the magnitude that we gain in LTP is equal to the magnitude that we lose in LTD with respect to the EPSP, right? So if a synapse is strengthened, where we may go from a, 5 millivolt EPSP to an 8 millivolt EPSP, that 3 millivolt change, right, that 3 millivolt increase in strength is reversed when LTD is initiated. How much LTD occurs? That same 3 millivolts. So we get back to our original synaptic strength. This is important, right, because I think it suggests that LTP and LTD act on the same site. Right, and so if we were to see, a 10 millivolt EPSP followed by a 15 millivolt synaptic depression, something would be different about those mechanisms, right? But the magnitude of each is the same. There are some similarities in the mechanism between LTP and LTD. So for example, they both require glutamate, so this is going to be glutamatergic synapses. They both require NMDA receptor activation. And they both are going to deal with important signaling that's triggered by calcium entry. Okay. Everything here that we just wrote down could be describing LTP or LTD, right? But let's look at how LTD works specifically. Well, in LTP, when we tetanized a cell, right, we saw an immediate jump in concentration of calcium. That calcium went up quickly because of the HFC, or HFS, excuse me, right, the high frequency stimulation. In this case, because we're only stimulating at 1 hertz, right, that's a pretty slow stimulus, the calcium signals are different, right? Calcium rises based on this stimulus, but the rises are slower and smaller. Than what we see in LTP after HFS, okay? And so what this triggers, we think, are calcium-dependent phosphatases. All right, so they're calcium-dependent, meaning they can't be active without calcium present. And once calcium-dependent phosphatases are active, remember what a phosphate does, right? It dephosphorylates substrates. It's the opposite of a kinase. So if there's some protein that's been phosphorylated to be active, a phosphatase would dephosphorylate the substrate to turn it off. We know this is a phosphatase-dependent process because when we treat cells with phosphatase inhibitors, we block LTD but not LTP. So phosphatase inhibitors, oops, what I'm trying to write here. Phosphatase inhibitors eliminate the LTD, but LTP is still able to be induced. Okay, so we have a good evidence that phosphatases are involved. Okay, and the way that we think this occurs, although we don't know all of the steps, is that AMPA receptors that are on the postsynaptic membrane get internalized. Endocytosis, right? The cell brings something back in, and in this case, it's receptor-mediated endocytosis. So that's a general term for any time that we can specifically target what's getting endocytosed, right? And so this internalization we think is a clathrin-dependent mechanism. And you remember clathrin, right, when we talked about synaptic vesicle cycling? So clathrin dependent. So what do I mean by clathrin dependent? Well, so if we look at this diagram over here, right, you can see that the AMPA receptors are in the membrane, right? And in order to bring those in, how is there specificity to that? Well, you can see there's a network of proteins in blue, right? And I'll try to trace those here to show you what I'm talking about, right? So there's this protein clathrin, right, which we think binds to the sites near where we're going to perform internalization, or where this cell is going to internalize. And what this signals, what this clathrin signals, is where the endocytosis happens, right? We don't want to internalize NMDA receptors, and we want to have some specificity toward this. And it's the clathrin dependent endocytosis that gives us that specificity, right? It gives us an ability to target what is being endocytosed. So clathrin, this protein that's surrounding AMPA receptors, tend to be the target for where the membrane then internalizes them, okay? And like I said, we think that this is a phosphatase dependent process, right? So if you follow the pathway, protein phosphatases that respond due to calcium changes, but slow changes in calcium, tend to dephosphorylate substrates. And again, we don't have all of the details of this pathway worked out, but the result is AMPA receptors that have been taken in, okay? Now this mechanism of AMPA receptor internalization that causes LTP is different than the one, or LTD, excuse me, is different than the one that we talked about in Purkinje cells in the cerebellum, and I'll talk about that again next. Oh, I forgot to mention this here. Right, so this is a figure that actually shows the LTD. You can see that in controls, right? We're getting about 100% of our controls when we stimulate the presynaptic cell and record postsynaptic response, whatever that is. Right, we call that 100%. So maybe we see an EPSP of 5, and then we get another EPSP of 5, and another EPSP of about 5. And after we induce LTD here by stimulating, right, 15 minutes, 1 hertz, then when we go and stimulate the CA3 neuron, right, the presynaptic neuron, the response of a CA1 is reduced, right? So the EPSP generated by the CA1 neuron here is only about, what, 60%? Or so, what it was before the low frequency stimulation, right? We used to be over here, and now we're over here at about 60%. So if we were getting 5 millivolt EPSPs, maybe now we're only getting 3 millivolt EPSPs. And we see this lasting for a long, long time, right? So we're out 75 minutes, and there's still this depression. Okay, let's talk about real quick, like because we did it before, what happens in those Purkinje fibers.